Hi, all. Today I would like to explain about the differentiability, linearization, and differentials. For the function of one variable, you know about the differentiability, linearization, and differentials. So, in the case of the first, we are going to define the differentiability. Differentiability. We are going to define the differentiability. So, in order to define the differentiability of a function of two variables, before that we have to recall the differentiability of one variable. Suppose we have y equal to f of x is a function of one variable. It is differentiable at x equal to x naught. Then we have to recall the definition. And what happened? Then the definition of this differentiability implies the change in the value of f that results from changing x from x naught to x naught plus delta x is given by the equation of the form delta y equal to f dash x naught into delta x plus epsilon into delta x, in which epsilon tends to 0 as delta x tends to 0. So this is the definition corresponding to the one variable. When a function y equal to f of x is said to be differentiable at x equal to x naught, then as x tending to x is changing from x naught to x naught plus delta x, then corresponding change will happen to y also. Then delta y equal to f dash x naught delta x plus epsilon into delta x. This is coming from, we know that this is delta y by delta x is approximately equal to, that is, which is same as, this is limit as delta x tends to 0, delta y by delta x is, which is equal to f dash x at the point x naught. Then we are saying that then delta y by delta x is equal to some x dash x naught plus epsilon. So delta y is equal to, this is the error term, right? Otherwise this is always not equal. So when we eliminate this limit, so then this is some delta x. Okay. So in order to equate this equation to this equation, we are adding an error term epsilon, which is greater than 0. So delta y equal to f dash x naught delta x plus epsilon into delta x. This is the origin. This is the way we have derived this equation. This is that way. Okay. So similarly, we can define the differentiability in the case of the two variable also. Okay, please listen. The theorem 3, the increment theorem for functions of two variable. Suppose that the first partial derivatives of f of xy are defined throughout an open region R containing the point x0, y0, and that fx, fy are continuous. at x0, y0. Then the change delta z is equal to f of x0 plus delta x, y0 plus delta y minus f of x0, y0. Here z is equal to f of xy. Okay. The value of f that results from moving x0, y0 to x0, y0 plus delta x, y0 plus delta y in R, which satisfies the equation. This is we have to remember. Delta z is equal to fx at x0, y0 into delta x plus fy at x0, y0 into delta y plus epsilon delta 1 delta x epsilon to delta y, in which epsilon 1 epsilon 2 tends to 0 as delta x delta y tends to 0. Look here. This is f dash x0 into delta x plus epsilon delta x. What is the difference between the two variable and one variable? Here one variable is added. So in the place of f dash x, here fx into delta x, fy into delta y plus there is only one epsilon, here 2, corresponding to delta x and delta y, epsilon 1 delta x, epsilon 2 delta y. This tends to 0 as this tends to 0. This is a increment theorem for the function of two variables. This is very important theorem, and using this we are going to define the differentiability. A function f of xy is said to be differentiable at the point x0, y0 if fx at the point x0, y0, fy at the point x0, y0 exist and it satisfies the equation. Delta z is equal to fx at the point x0, y0 into delta x plus fy at the point x0, y0 into delta y plus epsilon 1 into delta x plus epsilon 2 into delta y, in which epsilon 1 epsilon 2 tends to 0 as delta x delta y tends to 0. So this is a definition, and a function f of xy is differentiable at this point if this exists and it satisfies the equation delta z equal to this type of equation at the point x0, y0. F is a differentiable function. F is a differentiable function if it is differentiable at every point in its domain. The next corollary of the partial derivatives fx, fy of f of xy are continuous throughout an open region R, then f is differentiable at every point of R. It is differentiable if it is continuous throughout an open region R. Then f is f is differentiable at every point of R. One more theorem, theorem 4, very important theorem. If a function f of xy is differentiable at x0, y0, then f is continuous at x0, y0. How will you prove this? Write this as, here z is equal to f of xy, and we know delta z is equal to f of x0 plus delta x, y0 plus delta y. The proof of this theorem, we have z equal to f of xy. So delta z is equal to f of x0, y0. This is a definition, and delta z this is the function, given that the function is differentiable. So this definition also exists. So from 1 and 2 equate to this right hand side. So this is equal to fx into delta x plus fy into delta y plus epsilon 1 into delta x plus epsilon 2 into delta y. This is actually, we have x is equal to x0 plus delta x. So x0 plus delta x is x and this is y. So f of xy equal to, this goes to the right side, f of x0, y0 plus the remaining term. So we will get this question. This is equal to fx at delta x plus fy at delta y plus epsilon 1 delta x plus epsilon 2 delta y. So as delta x, delta y tends to 0, this term tends to 0, this term tends to 0, this and this term. This whole term tends to 0, so the remaining is f of x0, y0. That means as limit delta x tends to 0, delta y tends to 0, which implies limit x tending to x0, y tending to y0, f of xy goes to f of x0, y0, which implies f is continuous at x0, y0. Next, we are going to define the term, the linearization. Term linearization. Linearization of a function of two variables. So, how to linearize a function of two variables? Function of two variables can be complicated. So, in order to convert this, eliminate this complication, or in order to convert this, sometimes we need to replace them with the simpler ones. So for that purpose, we are going to linearize a function of two variables. So the linearization, the process is defined as L of xy. The linearization of a function f of xy at a point x0, y0, which is defined as f of x0, y0 plus fx at the point x0, y0 into x minus x0 plus fy at the point x0, y0 into y minus y0. The approximation means we are approximating the function with this L of xy. In some situation, the complicated function f of xy, we are replacing this by L of xy. This is a linear approximation. It is very simple to access. This is a standard linearization of linear approximation of f at x0, y0. This is a standard linearization, linear approximation of f at x0.